course, welcome to this online workshop on parameter estimation with Bilby, organized by the ICTS Astrophysical Relativity Group. I hope all of you are keeping safe and keeping yourself engaged, and this is one way of doing it. As you know, Bilby is a powerful new software tool for making astrophysical inference from gravitational wave data. It has already become quite popular among the gravitational wave astronomers, and I have no doubt that its popularity will only increase in the future. I assume that there are many people from inside and outside the LIGO collaboration and who can find very good use of this piece of software to make interesting inference from this wealth of data that is available to us right now, both for people inside the collaboration as well as outside the collaboration. And we are very fortunate to have the lead developer of Bilby leading this workshop as well. I'm talking about Greg Ashton from the University of Monash. And I want to first express our deep appreciation to Greg for doing this on behalf of all of us. Thank you, Greg. Also, Aditya Vijaykumar and Shashwat Kapadia have been spearheading the organization of this workshop, and this idea essentially came from them itself. So thank you, Shashwat and Aditya, for doing this for us. Many of us are also volunteered as tutors to help the rest of the participants, including Srishti Goyal, Nikhil Sarin, Mukesh Kumar Singh, Apratim Ganguly, Harsh Narola, Bhaskar Bishwas, and Arif Sheikh. And thank you very much for doing this. And I want also to thank the ICTS AV section and Naveen in particular for helping with this logistics of conducting this online workshop. So let me now ask Shashwat to perhaps introduce Greg and to moderate the rest of the workshop. I hope we will have an enjoyable and very useful workshop. Welcome.
Thanks, Ajit, and from my side as well, welcome everyone. It's wonderful to see so many participants enthusiastic about parameter estimation and gravitational wave astronomy. So I will very quickly introduce to you Greg Ashton, and honestly, this will not do justice at all because he's very accomplished already in his career as a gravitational wave physicist. So Greg has got his PhD from the University of Southampton and jointly from the Albert Einstein Institute in Hanover, Germany, which is also sometimes referred to as the AEI or the Max Planck Institute for Gravitational Physics. He then did a 2-year postdoc at the AEI, followed by a term as an assistant lecturer at Monash University, where I believe he is currently hired. Greg has had a number of highly impactful publications, including publications in Nature. His interests include, obviously, parameter estimation, gravitational wave parameter estimation, as well as various aspects of neutron star physics, not just limited to gravitational waves, but also to pulsars and pulsar glitches and things like that. He actually has, he's quite versatile because he's not only an excellent researcher in gravitational wave physics, but he also has considerable expertise in software development. And in fact, he is the core developer of the Bilby software, on which this workshop is based. And as Ajit mentioned, we have no doubt that Bilby will likely become the primary software for gravitational wave parameter estimation, both because of its power and ease of use. So without further ado, I'll hand over the stage to Greg Ashton.
Thanks so much, Shashwat. Really kind words, really nice. So thank you so much for that. And let me also just take the moment to say thank you so much to Ajit and Shashwat and Aditya for the invite to this workshop. I was really excited to hear about it. And I know there's so much excitement in the community at the moment. It's a fantastic opportunity for me to be able to chat to you all and hopefully teach you some stuff and who knows, develop some collaborations out of this. So I'm really looking forward to it all. So yeah, without further ado, I'll get into it. so if I share my screen, I think is probably the easiest thing, and I'll plan to go through some slides and things. So hopefully you can all see this. I'm just gonna get the chat open. Okay, I can't get the chat open, but if people want me, just please ping me or open your mic and ask questions as we go. I prefer to sort of get questions as I go rather than anything else. So I thought I'd just start off by sort of giving people an overview of what to expect over the next 2.5 hours and for tomorrow as well. So hopefully you have access to this GitHub page, which has some materials in it, which I put together with help from Aditya and Nikhil, and also other tutors sort of with suggestions and things like that. So on the main page here, you'll see that there was some pre-workshop material. If you didn't get to that, don't worry. There's nothing that can't be done within a minute or two, and we'll have an interactive session where you can get that done. And if you had problems with it as well, the tutors are experts on this kind of thing, so we'll be able to get you started, no problems. Then we have 2 sessions. We have today's session and tomorrow's session. And today's session is going to essentially try to go from an introduction to Bayesian inference itself to sort of gravitational wave parameter estimation more generally. And there'll be a notebook that we'll sort of go through, and we'll do that interactively with the tutors. So that will give you opportunities to ask questions and figure out all of the the regular hiccups of installations and various corner cases that we'll no doubt hit. So let's get going then. So there's a link here. So this just links to some slides, although they're not very detailed. But I thought I would just put a few things together just so we can all be on the same page. As I say, today's overview is Bayesian inference in general, and then we're going to talk to tutors. And so there's a link here to a notebook which has the slides which I'll actually be going through. So let me skip to that now. Hopefully you can see this okay. Just have one more try at seeing if I can get the chat open. I can never, there we are, chat. Okay, excellent. Okay, I can now see the chat, so please ping me in the chat if you need. Okay, so so as I say, I'll be going through this. So this is an introduction to inference with a hands-on approach. So none of this is going to be gravitational wave specific. The idea here is to do sort of inference basics. So we're going to sort of think about things like Bayes' theorem, stochastic sampling, and all of these things, which some of you will be sort of experts in already. Some of you will have no doubt heard of. But the idea is if we sort of see it in a simpler context where we don't have the full complexity of gravitational wave models to deal with, it's sometimes a little easier to get our heads around everything that's sort of going on, as we can sort of see the models and poke things a little easier. Okay, so let's go through this. So this is just installation. You don't need to do this. This is just if you're following along in the notebook, but you can do that offline, so don't worry too much. So what I want to talk about first up is about Bayes' theorem itself. And this is something, so if you're very familiar with Bayes' theorem, I sort of apologize in advance because it's going to be some detail about it, but I know it's something that people see quite often, and I think that it can be a little mysterious, and I'd like to try and remove some of that mystery around it and get people to think about it in simpler terms. Okay, so let's get on with that. So this is this Bayes theorem, which really forms the basis of everything that we're going to want to do. And it's a statement about conditional probabilities. So on the left-hand side, you have a statement which says the probability of A given B, and that vertical bar there, you really read as just given. So it's what's the probability of some event A given some knowledge about, about A, or it could be about, it could be unrelated to A. So let's give a really, really simple concrete example, which you have all no doubt seen something like this before. So if I have a regular set of playing cards, 52 card pack, and I ask you, what's the probability of drawing a red suit card from the pack? Well, of course, half the cards are red, so the answer is a half, right? It's easy. Well, how do you express that mathematically if you want to make some notation around it? Well, in this language of probabilities and conditional probabilities, we write it like this. We say that probability of the red card is equal to 1/2, and then we have this vertical bar and the I here says it's a normal 52 card deck, so a regular playing card set. So I here represents sort of background information, but it could also be a whole bunch of different things. So it might be, you know, we're going to be dealing with gravitational wave models. And so that, you know, the thing which goes on the right-hand side of that vertical bar might be, you know, some very complicated model that has sort of been coded up by people. But here, it's just a very simple statement that it's a normal 52 card deck. Okay, so then what if I make this a little bit more complicated and I say, well, what's the probability of drawing 2 red cards from a pack of 52? Okay, okay, you can all do this. It's pretty easy. I draw a little diagram out to help myself. So, you know, we start up here and we then have, you know, okay, either red or blue on the first one and then either red or blue on the second one. But of course, the slightly complicating factor is that on the second one, we don't have 52 cards anymore. So then you need to do a little bit of algebra, and you say, you know, the first one, well, that was 1/2. That was the one we did a second ago. The second one, well, I've already drawn 1 red card on the first one, so I now have 26 minus 1 red cards and 52 minus 1 total cards. So my probability on the second one is 25 divided by 51. And of course, you know, these events just, these probabilities multiply. So it's 25 over 102. Okay, super easy. So again, how do you express that mathematically? Well, what we actually want here then is this statement: probability of a red card on the 0th draw and a red card on the first draw. And this is, you know, we can just use this idea of conditional probability, which says that that thing, probability of red on the 0th draw and probability of red on the first draw, is this product of 2 terms. And this is exactly what you intuitively did when you multiplied those 2 terms just before. So you plug that all in, and so you end up with the answer 25 over 102. Okay, that's nice and easy, right? Well, that's nice, and that means that we all understand conditional probability. What I mean by that is that if I have the probability of 2 things occurring, so A and B, I can calculate that by asking 2 simpler questions, which is what's the probability of A given that B happens, multiplied by the probability that B happens, okay? That's missing a vertical bar there in that second term. Apologies for that. There's a missing term. Okay, so that's a nice statement of conditional probability, but we can write it the other way around, right? Like I didn't have to have, you know, this A, and then B. I could have done B and then A. And so I get exactly this term here. So now that I've done this, well, I look at the left-hand side of these 2 equations and I say, well, those 2 things are the same, so I can equate these, right? There's nothing wrong with doing that. So I can equate them, and if I just do a little bit of rearrangement, I'll end up with Bayes' theorem. So this is why I say it's just a statement of conditional probabilities. It's not a magic sort of formula. It's, you know, just something which comes out of saying that, you know, conditional probability is kind of the logic of how these things fit together. Okay, so yeah, my sort of fine joke here is that I don't think we should call this Bayes' theorem. It should really just be Bayes' one-liner or something like that. Okay, so thanks for indulging me on my aside on very basic probability theory things. I hope that was somewhat useful to some of you and not too basic to others. I think it's a nice way to get started thinking about what we'll be doing through the rest of this, which is, okay, we want to now use Bayes' theorem. We now understand what Bayes' theorem is. It's just a simple statement about events. And inference then is, or parameter estimation is really about figuring something out from the data. That's what we're doing. We're doing data analysis. We're doing Bayesian data analysis, then we use Bayes' theorem. So let's make some labels and let's make things kind of formulaic, if you like. So we'll now call data bold data, and we're going to now plug that into Bayes' theorem. Now, there's kind of 2 things you can do here, though, which is the first one is what we call parameter estimation, which is to say, I have a model and it has some model parameters theta, So in gravitational waves, this might be, you know, I have a waveform model that was fit to this numerical simulation or something like that. And it will have some parameters. So those parameters will be the masses, the spins, and so on and so forth. And you can ask then questions about those model parameters. You can say, well, you know, what's the best fit mass? What's the best fit spin? And so on and so forth. And, you know, what's 5914? You know, what's the best, how far away was it? And those sort of questions are what I refer to as parameter estimation. So you're figuring out the parameters from the data. But you can also ask what we call model selection questions. So maybe you have two models for the data. Maybe one is a binary black hole model, and one is a binary neutron star model where you allow for things like tidal interactions. And now you can ask slightly different questions, which is, okay, which of the two models best fits the data? And so we'll cover both of these in some short detail, but we're going to focus on the first one, parameter estimation. But I just want to sort of highlight that there is this other aspect of model selection, which is very powerful and something which comes out of everything that we do in this. Okay, so let's think now more about parameter estimation. So before I'd written out Bayes' theorem as probability of A given B, and then you have the right-hand side of that. Now what I'm doing is I'm plugging in some things which are more related or better related to the problem in hand, which is I have some model, I'm going to call it model A, and I have some data, which is always capital data, and I have theta, which is the model parameters of model A. So in the top line here, I've just plugged these in to Bayes' theorem. So I'm saying, this is parameter estimation. I want to know what the probability of the parameters are, the theta, given a fixed model and given some observed data. And so then on the right-hand side, we just applied Bayes' theorem where we switch over the data and the parameters. The model always stays on the right-hand side. That's a fixed here that we're always determining the parameters for a given model. So we can make this a little bit simpler. So the term on the bottom there of the top equation, probability of data given the model, this is in fact only a normalizing term. So you can see that it's just normalizing things so that you have a unit distribution. And so you can simplify this by essentially throwing that information away and saying, if I'm only interested in the left-hand side, i.e. the shape of the distribution, I really only need two terms, which is there are two things in the numerator. And those two things have names, and those are the likelihood and the prior. So the likelihood is written with this little curly L. So that's the same as the probability of the data given the model and theta above. We've just changed the P into an L, a little curly L, to fit with standard notation in the literature. And the likelihood really tells you, okay, if you give me some set of data, you know, a gravitational wave strain, for example, and you give me a model parameters, so some particular mass, then you calculate the likelihood. And that will come from statements about the noise in the system. So, you know, is it Gaussian noise, what kind of noise, and the PSD and things like that. You then have a second term, which is the prior, which we label with this pi. And that is your information about the model parameters before you see the data. So for example, you know, in gravitational wave parameter estimation, we have a parameter which is the luminosity distance to the source. Now we know that the luminosity distance of the source scales, at least for low redshift events, something like the square of the distance. And this is just saying that, you know, there's an equal amount of events in a given volume. And so if you sort of think of a sphere and you expand it out, that's how that scales. And then when you multiply those two things together, you end up with, on the left-hand side, the posterior. And that's the thing that in parameter estimation that we're trying to pull out, is the posterior distribution. Okay, so that's really the core of everything that we're going to try and do here, is to estimate that posterior. So now let's get into, you know, a specific example where we really do this. And I'm going to do this with, as I say, non-gravitational wave data. And in order so that we can sort of, you know, understand every little facet of it, I'm going to go through in detail how we construct that data and the model for it. So if things don't make sense as I'm going, please please ping me in the chat because I can give sort of a better explanation for it as we go. So, okay, so let's say I have some data, y, which is a vector, if you like, of observations, y0, y1, y2. So each of those is just a float, or a number. And I observe those at some times t, and so t is again a length n vector of the times which I observed it. So I may have a sort of clock and I measure it every half second, say, or something like this. Then let's define a model. And so this is just for the purpose of the demonstration. I'm just going to say that my model, model A in this case, is just a sine function. So I say that y, my prediction for the data, so this is my generative model, is that it's a sine function which goes as omega t. Okay, so I take the observed time. If you give me what the observed time is, and you give me the angular frequency omega, then I predict that y will be sine of omega t. So therefore, we have, in this case, just one model parameter, just the omega. That's the only thing that we, the only parameter that this model has. Now, of course, you can generalize this to have an amplitude and a phase offset and all sorts of things, but we're going to keep with a simple case. So, okay, so then we can code this up in Python, right? And so I'll just say model A, and it's just return sine of omega times time. All right, let's simulate some data. So the first thing we want to do is we want to, so we create basically two values which are sort of simulation values. So omega true is the true value of omega. And I also create a value for sigma, which is the noise in the system. And here we're just going to use Gaussian noise, so zero mean Gaussian noise with a standard deviation of sigma. So then I just go through the usual quick steps of create some time. So here between 0 and 12 and 100 values. I then evaluate my model, and I then add the random noise to it. So that's this term here. It's just adding Gaussian noise. And I plot this out, and it looks like this. It's a sine term with some scatter about it from the noise. Okay, nice and easy. This is now my simulated data. Okay, so next up, we want to figure out something from the data. And of course here, the one thing that we don't know is the frequency, the angular frequency omega, right? So we know, we simulated it, so we do know the true value, but let's pretend that we're just given the data and the model. What we want to do is figure out what that omega is. So what we can do is we then say, okay, well, the observed data we know is the deterministic model, which is the sine function plus noise. So we can invert this, and we can say that the noise is therefore the observed data minus the model. So in a sense, what I'm saying is if I knew exactly what the true model was and I subtracted that off of the observed data, I should be left with just Gaussian noise. And that statement by itself is enough to write down this likelihood. Okay, so this term here is how we define that likelihood. Okay, so I'm saying that the likelihood, if you give me a data point yi, ti, and you tell me what omega is, and we know what sigma is, and things like that. I think the sigma's changed between these two slides. Apologies for that. If you spotted that, well done. And then it's just a normal distribution where I subtract off the model from the observed data. So this is just the standard Gaussian distribution, subtract off that y ti, so the model minus the observed data. Okay, that's nice and easy. Now, of course, we don't have just one parameter, one data point, but we have many data points. And we, in general, just product those together because they're independent data points. And in general, we don't want to use the likelihood itself, but we rather use the log likelihood. And the reason is just numerical stability. We find that these things, you get very large numbers. And when you're dealing with large numbers, it's much easier to use a log of the number rather than the number itself. So we turn that into a log likelihood, and we say that, okay, the log likelihood of all the data is the sum of the log likelihoods of each individual data point. Okay. So that's what we then need to code up. That's the likelihood that we need to evaluate when we want to understand the likelihood of omega. Okay, so let's code it up. So here, the top there, I have a function. The function takes in the data, so y-obs and time. It also takes in the omega, so the point that I'm currently interested in, and the sigma. And we then, okay, so we say that, okay, ya is the model. And we evaluate the model, we then just code up. So this line here is just exactly evaluating the log likelihood for each of the data points, and then we sum over those log likelihoods. So once we know how to calculate a log likelihood, we could just evaluate that over a grid of points in omega. And so this is what I've done on this plot here, is just evaluate that on a grid of points. And you see that it peaks at the right value, okay, or around the right value. Now, that in general is parameter estimation. That's enough. We haven't bothered with the prior here. We could add in the prior, we could multiply by the prior. And if our prior was informative, so say we had some reason to believe that omega, followed some distribution that wasn't uniform, then we'd need to encode that to get to properly capture our posterior. But you could code that up and do this with a grid. Okay, well, we can take the maximum of the likelihood. So just pull out the maximum likelihood from that grid of points and plot it out. And this is a very useful exercise. And this is what's sort of referred to as posterior predictive checking, in that you take some output of your parameter estimation and you then go back to the data and check that it makes sense. So here what I've done is I've taken the maximum likelihood point. I then evaluate my model at that maximum likelihood point, plot it through the data, and yeah, it's a pretty good fit. There's some noise in it, but I believe that as a good fit to the data. Now, okay, as I say, that was just using the maximum likelihood, but of course we have this prior term as well. So we can, as I say, enfold this prior information in, but what we can also do is if we have a uniform prior, we can just ignore it because effectively, the pi of omega is a constant, so you have that. Now, in general, don't do this, but this is just for the purpose of this sort of illustration. We're just going to have just the likelihood as well, and we'll see in our examples later on how to include that. But just for kind of seeing the basics, I'm going to throw the prior away, and we'll just deal with the likelihood for the second. Okay, so the next thing then is we take that log likelihood, and we can now have our log posterior, and we normalize it. So we threw away the normalizing information before. We can now just normalize it in order to have a proper normalized posterior. And now that we plot it not in log space, we see that it's actually off a little bit from the true value. I'm going to talk a little bit more about this now. So why is it that the peak is not consistent with the true value? Why does the likelihood not peak at the true value? Well, it's because we introduced noise, and the noise gives us uncertainty, right? So we know that if we have a very unlucky realization of the noise, we actually might be quite far away from the true value. But in general, we should be around the right place. But how would you know if you just look at the median, if you like, of the distribution? How would you know that you had peaked at the right place? How would you sort of quantify that? Well, the Bayesian way to do this is something called the credible interval. And so what you're interested in is essentially that the value of omega lies, say, with some probability 95% between two values. So how do we figure this out? Well, to do that, we turn to the definition, which is the cumulative distribution. And you essentially say that you look for an interval in the cumulative distribution which includes 95% of the posterior. So this is just the posterior. Sorry, this is just the cumulative distribution. I've just used the NumPy cumulative sum function to calculate that. And you can then just pull out from that the 2 points where the cumulative distribution passes through 0.05 and 0.95. So this is, in fact, the 90% credible interval because it's 95. So 0.05 to 0.95 is, of course, the 90% credible interval. And if we then plot that out, we then see, okay, we have a range of values which are consistent, and that encompasses this broad peak. So if we reran this simulation choosing different random realizations of the noise, we'd find that peak moves around, but 90% of the time it would lie within that credible interval. Okay, so that's kind of parameter estimation in the most simple way, which is just using a grid, right? We just evaluated the the likelihood on a grid. And you know, it made sense. It was easy to do. If you run this, it takes just a few seconds, even that fractions of a second. Now, one of the things that you...
Can I ask a question?
Yeah, please do, yeah.
This frequentist interpretation of the posterior, this PP plot, is it valid in all cases, or does it require some conditions?
So this is a Bayesian interpretation here. Do you mean that the
claim that the 90% of the time this true value lies within the 90% credible region? It's like a frequentist interpretation, right?
Yeah, sorry, you're correct. You're right. I'm mixing things up here. So I think that the Bayesian interpretation would be, yes, that you have 90% credible interval, that you have a 90% probability that it lies within that. I think that in general, in this case, and now you're I don't have a good answer as to whether this is consistent with the credible interval exactly. So there's with the confidence interval, which sometimes is sort of mixed up. I don't think that they agree all of the time. And there's certainly edge cases where those aren't the case. I think I default to using that as it's a kind of easier way to understand these. And certainly in cases like this, it really is the same. But I wouldn't say that those are the same in general. And I'm sure there's a good literature which discusses this.
Okay.
Does that make sense?
Yeah. No, I wanted to say, like, under what conditions the PP plot is diagonal, but I guess it just probably depends on a lot of details, I guess. I don't know. Yeah, thanks.
Yeah, I mean, I think in general, it should be the case. And I think that it comes down to more more sort of fundamental difference in understanding of what probability means. For me, I think this is a good interpretation and a sort of an easy one to grasp rather than trying to get into the details of probabilities.
Okay, thanks.
Okay, so we did this with just a grid of points, and so then a kind of interesting question is, well, what happens when things are more complicated than, we just had one parameter here? What happens if I'm in 2 dimensions or 3 dimensions, or in a gravitational wave problem, we typically have something like 15 dimensions? Well, this is very much the sort of what's often referred to as the curse of dimensionality. So you can imagine trying to find, if you doing a sort of search for a point on a line, something like a bisection method where you divide it in half and is it in one half or is it in the other? That's pretty quick, right? It's easy easy to do. Now imagine doing that in 2 dimensions, and now you can see that immediately the problem gets much harder. You divide it into 2 in the 2 dimensions, but immediately you now have 4 sections to go and study. And as you go up in dimensionality, that is scaling with the number of dimensions, so to the power of the number of dimensions. And so that's really what people refer to as this curse of dimensionality, which is in a handful of dimensions, these kind of searches where you say bisect or just evaluate a grid of points, they work. But as soon as you're up to sort of 10 dimensions, they're just completely impossible and computationally very inefficient. So that's where we turn to stochastic sampling algorithms. Now, we'll say that there are many other sort of ways to approach this. So, the higher dimensional search problem of finding the maximum likelihood point is very well studied in the literature. But in Bayesian inference, we're not just interested in the maximum likelihood point, but we're interested in the shape of the distribution as well. And that adds a kind of another dimension to this problem, that you not only have to find the maximum likelihood point, but you actually have to explore the region around it. And it turns out one of the most efficient ways to do this is stochastic sampling, where you draw points from that parameter space and try to draw points which are effectively draws from the posterior distribution itself. So I'm going to go through this with sort of a quick example, if you like, of building one of these from scratch. And then we'll see how to just use Bilby as a sort of a box which will do that for us. But I want to give you some insights into how things work if you were to sort of build it yourself from scratch. And that will give you some sort of ideas when we're down the track and you've run Bilby on things as to what might be going right or going wrong. So the first thing you might do is you might say, okay, let's build a peak finding algorithm. So it's just an algorithm which finds the maximum likelihood peak to within some precision. And so the way that you might do that is you might say, well, let's just pick a random starting point. So I don't know where to start, but I'll pick a value of 1.16. I don't know if that's close or not, but it's a good start. You then evaluate that likelihood, right? So we evaluate the log likelihood function that we defined before. And we then say, okay, I'm at this one point. Now let's take a random jump, okay? And so I take a random jump. And this time, the random jump in this particular example, so if we're looking at the plot here, takes me in the right direction. And so I say, okay, I've gone in the right direction. If it's higher log likelihood than my original one, then I will continue in that direction. So I basically evaluate this loop, and it's sorry, I should say, if it's not higher than the log likelihood, I throw it away and I ignore it, and I start again. So I basically keep drawing points until I draw one which goes uphill in terms of the likelihood surface. And this will then, if I just continue taking steps along this path, this will lead me to the maximum likelihood to within some precision. And you can estimate that. I'm not doing that here, but that's the point of this thing, is that if I take random draws and I only ever go uphill, I'll get to somewhere close to the peak within some specified amount of time. Now that's useful, but it doesn't tell me about the shape of the distribution. So how do we make it so that it can tell me about the shape of the distribution? And in particular, what happens if I have sort of things which are multimodal and have two peaks? I might end up walking up one peak and there's a much higher peak over here. So now we're going to build a very basic Metropolis Hastings sampler. And the idea here is to introduce randomness, which means that we don't always walk uphill, but we sometimes walk downhill. So how do we do that? Well, we take our algorithm that we had before, our peak finding algorithm, and we add a random element to it, okay? So what we do is we pick a random point, and then we say, okay, if the log likelihood is higher than my last one, plus some random number, which I draw from a uniform distribution, then I accept that proposal. What this means is that because of that random number, I'll sometimes step downhill. And the amount that I step downhill and the amount that I step uphill happen to be in the right proportions that the end set of samples will be draws from the posterior distribution. Now, there's an important point here, which is that when you step uphill, sorry, when you reject the step, so if you say draw a point which is a bad point and the random number doesn't help you to accept the point, you still keep a hold of that point, okay? So you end up with a list of points with many repeated elements to it. And this here, so the plot, you can see those repeated elements, so you get stuck for some finite period of time at a point before moving to the next one. And this is the basic of an Mcmc sampler, and this will give you samples drawn from the posterior. Now they'll include many repeated points, but in general, if you pick a random point from it, it will have the right proportions of the posterior distribution. And we can plot this out. So I take the output of this this run here, and I run this in fact for a little bit longer. So that was 100 steps before. Run it for 10,000 steps. Still, things are starting to look a little better. It's still getting stuck in for some periods of time, but in the right proportion, it's doing that. And if I take all of the samples from that and I plot them in a histogram, I end up with this, which is a nice representation of that posterior distribution in exactly the same way as we did it with the grid before. We're now doing it with a histogram. But the key is that rather than having exact, I don't have a functional sort of functional evaluation of the posterior. Instead, what I have is a list of samples. So that's these omega values. And I need to bin them in a histogram in order to get the posterior. So this is, the point here is to say that, when we run our stochastic sampler later on with Bilby, that will be the output. The key output is going to be a bunch of random samples drawn from the posterior, which we can bin into a histogram. Now, one of the differences that we'll do when we operate with Bilby is, these omega values, as I say, have many repeated points in them and have other sort of subtleties to them. What we do is we do cleaning on that. So you remove the right proportion of values, so you end up with a set of independent samples without repeated values. Okay, so these are kind of, just a very sort of brief introduction to sampling. And, as I say, this was a very, very simple algorithm, and it had many, many sort of problems with it. So I'll just talk briefly about some of those problems. So you see that one of the things that we did was we drew a random number from a normal distribution when we wanted to pick a new value. So when we wanted to sort of jump, we had to pick a new value and say, okay, I'll jump, plus or minus 1 or something like that. Now that's going to depend on the value that I'm sampling in, right? So if I sample in say I'm sampling in chirp mass, if I sample in the solar mass, then I'll need to have a particular distribution to draw from. But if I sample in sort of kilograms, well, it's now 10 to the 30 or something like that. It's a scale of numbers, so I'll have to draw from a different distribution. So there's a scale problem there. And so you have to tune your MCMC to the right scale of the problem that you're sort of working in. Now, the advanced MCMC methods and nested sampling, which Bilby wraps up, have fewer tuning parameters. That's one of the reasons why we use them, is that people have thought long and hard about many of these problems, and they implement sort of clever techniques, which I'm not going to go through now, but you can sort of go to the packages and they have nice sort of descriptions of them. So things like parallel tempering, they use ensemble samples where you have a whole sort of cloud of points which move around, and things like that. We then also have nested sampling, which is a slightly different way of doing this stochastic sampling, but gives you the same thing in the end. And this, again, this is the main one that we'll be using, which is something called the dynasty sampler. Now, just a sort of a high-level overview of the difference between MCMC and nested sampling. In general, MCMC should be faster. That takes less likelihood evaluations to get the same number of posterior distributions. But it's not sort of set up to calculate evidences. You can do it, but it's not the best thing. So if you want to do model selection where you need evidences, it's much better to use nested sampling, which is it's sort of designed to do evidences by design. And one of the things that we find in practice is that nested samplers tend to be a little better at getting things like multimodal distributions and funny shaped posteriors. Okay, so I am going a little slow, so I'm going to try to speed things up so we make sure we have lots of time for the sort of interactive elements of this. So I've given you a kind of whistle-stop tour of Bayesian or Bayes' theorem, stochastic sampling, and the basics of, okay, I want to, how do I report things from stochastic sampling? So things like credible intervals you can do with your set of samples, medians, and all of that. So now we'll get into talking about Bilby. And as Ajit said in the introduction to this, it's a sort of generic Bayesian inference library, but it is specialized around gravitational wave transients, and we'll be using it for gravitational wave transients throughout. But before we get into that, I want to show how you would apply it to the simple setting which we looked at before, just so you can see where a sort of translation of the things that we've looked at so far and what we'll be doing in the workshop, and it's not sort of such a jump. So okay, so the idea is we're going to use Bilby to repeat what we did before. So we firstly, we had to code up the likelihood before, right? We had to actually define sort of all of the different maths of it. Well, one of the things that Bilby does is it gives you an interface to a likelihood object. So this is all you need to define the likelihood in Bilby. You say there's a nice Gaussian likelihood which is coded up, and you just give it the data, you give it your model, so that was the functional form of the model, and you give it the noise. Now you can actually create your own likelihoods, and we have sort of examples to do that, but most of the common ones like Gaussian likelihoods are coded up already. So, okay, this is just redoing the first steps that we did, which was let's evaluate the likelihood on a grid, and this is just showing that the likelihood which is coded up in Bilby is the same as the likelihood which we coded up before, and things agree nicely. No Bilby is the same as Bilby, so that's good. So now, okay, let's because it's easy to do in Bilby, we're going to make things more complicated, and we're going to look at the sort of full case of having 3 unknown parameters: an amplitude, the angular frequency which you had before, and the phase offset. And we're also going to include the sigma uncertainty as well. So, okay, so this is how we do this in Bilby. So we're going to define a new model, model B, which now has these extra parameters. So the omega, A, amplitude, and the phase offset. We'll plug that into our likelihood. And now we have priors. Okay, so before we kind of threw the prior information away because we didn't want to code it up. But in Bilby, it's very easy to code it up. What you do is you create a dictionary. It's just a regular Python dictionary object. And you essentially say, okay, I want A to be a uniform distribution between 0 and 2. Now, there's many other distributions which are available, things like, sign distributions, Gaussian distributions, anything you want, mostly are there. So, okay, so we there define these priors, and we then run the sampler. And this is what, this is the kind of core of Bilby, is this run sampler object here. So what you do is you pass it in a likelihood and the priors, and then a few kind of parameters, or values, I guess, which are just for sort of setup. So things related to how to sample, the number of live points, and some other things like that. You will then run it, and you'll get some output. We'll see that output later on. And this is what you'll get back. So you return a result object. So this is, sorry to skip back and forth. The run sampler gives you back a result object like this. And that result object has a number of different things you can kind of do with it. So an easy one is you can plot the corner plot. It's falling off my screen a little bit here. Sorry about this. These are the kind of corner plots that you're probably used to seeing. They show you this sort of higher dimensional parameter space. And you can see here that, it's not a sort of perfect capture. And this is, again, because of the noise. You get some variation. Aditya asks, why do we need a prior on sigma? So in this case, we happen to know what sigma is. When I was writing this example, I was just wanting to demonstrate that if you didn't know what sigma was, you can plug that in as an unknown parameter. So it's really up to you whether you decide to put it in or not. It depends on the problem in hand. If you have some so you have some X-ray data or something like that you want to analyze, then you might know what sigma is because of studies on background off-source data. But on the other hand, you might also have uncertainty on it. So you may want to include sigma as a model parameter. As a sort of, I guess, relation to gravitational wave parameter estimation, we know what sigma is in the sense that we use a PSD. But in fact, there is uncertainty in the PSD, and an active area of kind of investigation is how to include that uncertainty into the estimation. So in fact, including PSD uncertainty is a huge area of sort of study at the moment. And reflective. Oh, that's okay. This is okay. I wrote these slides a while ago, and this is an old keyword that we used to kind of use. You ignore that. You don't want to use the reflective prior boundary. There is some sort of technical detail about, so there is periodic boundaries and reflective boundaries, and it's effectively what happens when the sampler gets to the edge of the prior space. What does it do? Does it just throw the point away, or does it, return the point reflected or wrapped around? I think here you'd actually want a periodic boundary because pi goes to minus pi. Here it's the sampler which is being used is dynasty in this case. That's the default when you run sampler. You could specify that with sampler equals dynasty or some other thing. We'll see examples of how to set that exactly in a moment. Okay, and then Sohan says, what happens if you change the value of nlive? So nlive is the number of points that you use to do this parameter range. So in general, you want a minimum of sort of 500 live points. If you have more, you'll end up, you'll get a better estimation of the posterior distribution. You will, in general, take much longer to do it. So it scales with the number of live points. So you want to basically pick a number of live points which is sufficiently high to capture all of the features but not so low that but not so high that it's sort of too slow. If you go the other way and you set nLive to be too slow, effectively what you're doing is you're throwing 500 live points down into this space, and you're using those to sort of capture the features. So you can imagine, if you only have a handful, say 10, there just won't be enough live points to sort of capture the features, and you basically, the sampler will not give you proper outputs. Suvik asked, what if the sigma is different for each point? That is a very interesting problem. You can code that up. That's and so there's not just, what if sigma is different for each point, but what if they have uncertainty in the x direction as well? So it's a different likelihood. You could code that up. In fact, I think the one where you have just uncertainty in y, but an array of values, you can pass those in. So if you look at the help function for the Gaussian likelihood, it should tell you if that's possible or not. If not, you can code that up basically. Are the injection parameters starting guesses point value? No. So the injection parameters that I'm passing in here, these are just used for plotting purposes. So this is just so that when you make this plot, the orange lines show up. That's all they are. Okay, so what is the confidence interval different boundaries in 2D marginalization plots? Okay, there's tons of great questions. Keep them coming. Okay, let me just, okay, so in this plot here, these are 1, 2, and 3 sigma. You can set that. That's the help for plot corner. How many dimensions has Bilby succeeded in performing PE? So I've done things, so we have, standard gravitational wave parameters estimation, which is up to sort of 70 dimensions, but not all of those dimensions are interesting. So a lot of them are calibration parameters. So I think that, it's probably better to say that that's something like 15 or 16 parameters. The samplers which we have coded up, so things like dynasty, have been used in high dimensional spaces, 50 to 100. And there's, I recommend you go and look at the sort of papers which are written around that, because they have much more discussion on that. So yeah, if the prior ranges are large, will nLive also need to be large? So in general, yes, you probably want, I would say no. In fact, you should probably just go with a standard of nLive of 500 or 1,000. If you're just doing something which is sort of quick and dirty, 500 is fine. 1,000 we found works very well for typical gravitational wave parameter problems. But one thing I will say is that if your prior ranges are large, it will make the run slower. So in general, nested sampling the time it takes to run is from going from the prior range to the posterior range. And so if you make your prior range larger, it's going to be slower. Okay, there was a question I missed. Apologies. Okay, is it normal practice to set the prior as uniform distribution for all the parameters? It's something a lot of people do, but you really, you should really choose your prior based on your astrophysical or your physical understanding of those parameters. So, for something like this, okay, the angular frequency, I chose a range between 1 and 1.5. As long as the 1 and 1.5 are sufficiently far away from the posterior sort of width, that it's not going to sort of hit on the edge, then that's a reasonable range. And of course, my prior range could be, my sort of real prior range might be much larger than that. But, if you have information which you should include, so for example, you have sort of previous observations or some reason to believe, that it, follows some particular shape, you should use that information and that will improve your inferences. Okay, has Bilby been used in low latency and multi-messenger research like the SPEAR pipeline? No, so nested sampling and these kind of full PE things are just so much slower than anything you could do with something like SPEAR. So those are really, planned to be, as fast as possible. And they're talking about, producing results in sort of milliseconds. If you want to do that with sort of full parameter estimation, you need to use a sort of machine learning approach. Those are the only ones which have any promise to sort of get you answers within a few milliseconds. The sort of times that we'll be talking about will be, of order a day to run on something like a binary black hole system. There is, there's parallelization, which can reduce that wall time, but at the cost of huge computational cost. So it's they're not kind of comparable, and they're kind of answering slightly different problems, which is, for low latency multi-messenger astronomy, you just want to know what the sky localization is to within some fraction. For the kind of things we're interested in, we really we want to get the best answer we can within a month, and that's the timescales which we're typically talking about. For multiple detection, do you recommend tying it with likelihood or recursively running with modified? So you mean if you have like multiple data sets? You can do both. It's an really interesting question, and I don't have a good answer because I think that's an interesting research topic. If you can sample everything all at once, it's always better to sample everything all at once. But it may not be possible to do that, so it may depend on the problem in hand. And then Nirvan asks about these convergence criteria. So this is something I haven't really got onto yet. We'll talk a little bit more about it tomorrow. There's defaults kind of set up in Bilby, which are intended to work for gravitational wave events, and we have a sort of review that's ongoing and wrapping up at the moment, where we'll we have sort of suggestions for the recommended defaults. But in general, it's a little bit of a black art, and it needs some experience, and you need to sort of run things, look at outputs and convergence plots. And there is never a guarantee that your stochastic sampler has given you correct samples from the posterior. You always need to check things and do your best efforts to kind of rerun it, compare two different runs, check for stability and things like that. Okay, I'm going to get through the last few things because there's just a few slides left, and then we can maybe go to some more questions. So Bilby has these, so we returned this result object, and I'm just going to go through quickly what is kind of returned, just so you know how to use this thing. So the result object is returned, and as I said before, the thing that we're really interested in is the samples themselves, and those are stored in this thing called the posterior, which is a pandas data frame. You can sort of print it out, and you can pull those values out and sort of do interesting things with them. So for example, you could plot them in a histogram and plot the 90% credible interval. And that's what I'm doing here. So using the NumPy quantile method to calculate the 5% and 95% intervals, and also the median, and plotting this out. And so this kind of recovers what we did earlier with the grid method, but using Bilby to do it. And so it's, as you hope you can see, it's kind of a little bit easier as there's less coding up of likelihoods and things like that. Okay, I'm going to skip over this because we're sort of short on time, but you can also, plot things out, plot the maximum likelihood and sort of draws from the posterior and things like that. I'll leave that for people to have a look at in their own time. And there's various sort of metadata, but I think we're going to get to that today. So the only other thing I think I wanted to touch on was these trace plots. So there's kind of two things that you're going to see when you run today, which is the output from the sampler as it runs, which you'll see as this d log z, and I think your tutors will be able to talk you through what all that means, and we'll actually talk about it more tomorrow, and also these plots. But just to address Nirvan's sort of question there, which is about the convergence criteria and things like that. So these are the plots which I think are really powerful for checking convergence. So unfortunately it's cut off here, but these are the diagnostic plots which Dynasty creates, and one of the reasons that Dynasty is actually very useful. And you can see here the nested samples. So each point on the left is a sample that a point that you evaluated, and it's log likelihood. And you can see that it sort of funnels down to the right point. And these are very useful. So if you see these and these have sort of multiple sort of traces on them and nasty things going on, then that's a sort of indicator that you have poor convergence. If you see something like this, you can be very confident, you know, this looks like very nice and it sort of found the right point and sampled it well. Okay, I think that's basically it. So there's just a few, and Shrashti asked, sorry, what is the color axis? Okay, so the color axis on these trace plots is essentially where the posterior samples are drawn from. So the more orange it is, those are the points which you actually draw, which you actually use in your posterior distribution. So this is coming from the way that nested sampling kind of works. And I don't want to go into too much detail, but effectively, you know, the things which you draw initially are going to be weighted down. And the things which you draw at a certain point, which is this sort of orange band, those are the ones which are the real posterior samples. And at some point, it kind of funnels in on the maximum likelihood, and you don't weight those up because otherwise you'd have a sort of too much of a peak. So it's basically the weights which are used in nested sampling, if you've seen those before. Okay, great. And so I'll just go through these last few bits. So as I say, you can sort of print out things like log evidences. That's useful for the model comparisons if you do that. You know, all the different sort of metadata which is stored in it. And I encourage you to sort of just look through that, you know, use the sort of tab function in IPython notebooks to find out what's stored, because there's tons of stuff, tons of useful information. And with corner plots, you can do things like, you know, adding the corner plots, adding the injection values by hand if you didn't store them in the first place, plotting them without the truth values if you just want to, you know, if you don't have true values, for example, you just pass in a list of the parameters that you want to see. And so then I have this sort of discussion on priors. I'm going to pause here though and say, I think, is it better that we go to the interactive session? Because I think we're going to probably cover most of these things in that. And I realize I've sort of gone well over time. So unless anyone objects, I think it's best that we go now, and I will get people set up with the interactive session. I don't hear any objection. And so just to be clear, you know, if you want to look at that notebook, it's available. Let's get out of this. So if you go to the GitHub page that we have and you go to notebooks, you'll see there's 3 notebooks there. It's the Introduction to Inference one, if you're ever interested. But okay, so now I think it's a good time to get onto the interactive sort of segment here. So there's this page here. So getting started with Bilby simple BBHPE, which is what we're going to cover today. Okay, so there's 2 kind of parts of this. So first is the installation setup. Now, many of you may have gone through this already. So there's a few sort of steps, and there's 2 methods you can use to do this installation. I'm not sharing anymore, am I? Apologies. Let me share my screen again so I can show you what I'm pointing at. Yeah, so on this page, let me go back and talk you through this. So on the overview page here, and I'm hitting on the getting started with Bilby. So the interactive session here. So they say there's 2 methods to do this. So one is you can use IPython notebooks or Jupyter notebooks, as they're now called, locally. And if you have things installed, you can do that. However, there are some sort of lingering issues with Matplotlib. So if you experience things like that, we're fixing those at the moment, but unfortunately we don't have a release which those are fixed in. So massive apologies for that. If you want to do it with the notebooks locally, please go ahead. But the kind of safer option is to run things in the cloud. And so I'm going to talk through quickly just how you do that, just so we can make sure that we are all kind of on the same page. So what you do is you head to this page, which is colab.research.google. If you just Google Colab, I think it comes up. You'll need to log in with your Google account. If you don't have one, they are free, but yeah, probably if not, you'll, I guess, have to run things locally. So you then hit this GitHub tab, and you then need to enter the URL, and the URL is just this part of the GitHub page. So Gregory Ashton /GW parameter estimation workshop. If you hit enter, It will then bring up the 3 notebooks. And I think the one that we want to start with is the parameter estimation open data tutorial. So if you then click that, it will take you through and you'll have a live version of the notebook running in the cloud. So there's kind of no setup with this. And the only thing that you need to do to get started is just remove that comment of this one and hit enter. It will then say, you know, this warning, something or other, but it will install the software. And so that's all you need to do to get started. So, okay, so I think then at this point, Shrashti, am I right that we're going to go into breakout rooms? So I'm going to stop sharing. And I think that if we go into breakout rooms and we just sort of ask questions and run through this and use the tutor's sort of knowledge and expertise.
Okay, yeah, I guess this is a good time to go to the breakout rooms, unless there are any pressing questions from the participants at this moment.